Have you ever pondered about the nature of wave functions in quantum physics? The concept might seem intimidating at first glance, but it's not as complex as it appears. Wave functions are usually represented by the symbol ps or xt, denoting that they are functions of the coordinate x and time t. However, don't be mistaken, ps(xt) isn't a real function. In fact, it's a complex function, with the Schrödinger equation yielding complex solutions. It's important to note that the wave function of a particle at a specific time holds all the available information about that particle at that moment. But the wave function itself lacks physical interpretation and isn't measurable. On the other hand, the square of the absolute value of the wave function does have a physical interpretation. In one dimension, we interpret ps(xt) circumflex 2 as a probability density. In layman's terms, it's the probability per unit length of finding the particle at a time t at position x. Now, to make sense of this probability interpretation, the wave function must meet certain conditions. Firstly, it must be single-valued and continuous. Secondly, the probability of finding the particle at time t in an interval x must fall between 0 and 1. Also, it's crucial to be able to normalize the wave function. This means we should be able to select an arbitrary multiplicative constant in such a way that summing up all possible values, ps, t, 2 by xi yields 1. Essentially, the total probability of finding the particle anywhere must add up to 1. Furthermore, one of the simplest operations that can be performed on a wave function is squaring it. This gives us the probability per unit length of finding the particle at a time t at position x. For energy eigenfunctions, this probability is independent of time, since the square of the complex function of time equals the real number 1. To summarize, wave functions are complex functions that carry all the available information about a particle at a given time. They lack physical interpretation, but their square's absolute value does have a physical interpretation. The wave function must meet certain conditions for the probability interpretation to make sense, and one of the simplest operations we can perform on a wave function is squaring it. This fascinating realm of quantum physics reveals the intricate dance of particles that make up our universe.